My name is Ran Goldblatt. I'm the Chief Scientist of New Light Technologies. And I'm thrilled to introduce our keynote speaker, Dr. Chris Elvidge. Anyone who has ever worked even a bit with nighttime lights is familiar with his work and appreciates his invaluable contribution to the field of remote sensing in general and the use of nighttime lights in particular. I think that his 21,500 citations as of today, according to Google Scholars, speaks for itself. Dr. Elvidge started working with satellite low-light imaging data in 1994, initially with DMSP-OLS and then with VIIRS. Most of us working with DMSP-OLS have been using his annual composites that he developed, which provide evidence of 21 years of changes in nighttime lights emission in almost every location on Earth. Many of us also rely on his methods for intercalibration of DMSP-OLS. These DMSP-OLS and VIIRS nighttime light data are now widely used in an endless range of fields ranging from biology, urban sciences, economics, astronomy, and more. Dr. Elvidge was instrumental in establishing the DMSP Digital Archive at NOAA, and he led the media migration needed to retain the digital records. In 2012, Dr. Elvidge conceived of and led the development of VIIRS Nightfire, which is a global multispectral nighttime fire product, which is currently the only global fire product reporting temperature and source area on 24-hour increments. Dr. Elvidge is currently a senior research associate and the director of Earth Observation Group at the Colorado School of Mines, where the data he produces continues to advance almost every scientific domain. So now, without further ado, I will hand it over to Dr. Elvidge, who will discuss some of his recent work in exploring annual cycling patterns of nighttime lights in India. At the end of his talk, we will have a few minutes for Q&A, so please put your questions in the chat during your talk. Thank you, and Chris, over to you.
All right. Well, thanks so much for the introduction, and it's my pleasure to talk to so many people that are either interested in or making use of the data products that we produce. And with that, I'm just going to put the presentation up. Okay. You can see it? I'm trying to go to the, yeah, there. Looks good.
Yeah, it's fine. We can see it.
Great. So I have a small group at Colorado School of Mines with Fengqi Su, known as David, Mikhail Zhishin, and Tilotoma Ghosh. I see that on the line is one of our former members, Kim Baugh, who is instrumental in developing the methods that I'm going to show you that we continue to use. But we moved from NOAA to Colorado School of Mines about a year ago. Kim and I were at NOAA for, I think it was 25 years. So I had 21 years of service to the federal government and was eligible to retire and felt this was a good time to get back to an academic environment. So we're going to talk about remote sensing of lights at night. And obviously there are different types of lights. There's lights from cities and towns, industrial sites. There are also lights from things like fishing boats. And then there are things that get detected by the instrument that are not from electric lighting, but still creep into the data, and we have to try to filter them out so that we can look at the electric lights, things like gas flares and fires. So I'm going to give you an overview of this low light imaging that comes from meteorological satellites, from DMSP to VIIRS. I'm going to give you some insight into how we make these products and tell you about some of our upcoming product releases. We have, we're extending the DMSP time series with pre-dawn data collected by 2 or 3 different satellites, and that's funded by the Development Agency of France. We're getting ready to release a new annual VIIRS Nighttime Lights time series spanning 2012 to 2019. And we're in a position where we can finish up 2020 before the first quarter of the new year. And then I'm going to show you results that we have where we found something very interesting in India. That is annual cycling of the brightness of lights. And that's research funded by the Rockefeller Foundation. So the VIIRS is the Visible Infrared Imaging Radiometer Suite, and its primary mission is weather prediction. So the spectral bands were picked by meteorologists, the spatial resolution, the repeat cycle, and we're so lucky we have this billion-dollar instrument that the US government built and flies and brings the data down and prepares the data for so many users. And so we really have to acknowledge the huge investment that they make to get us this data. But the VIIRS, this is a daytime image. It has 22 spectral bands in visible, near infrared, shortwave infrared, midwave, and longwave infrared. And it does something very unusual at night in that it collects what we call low light imaging. And it actually does a million-fold amplification of the signal in the visible band. And so there's only one spectral band that gets this light intensification. And it's to meet a requirement coming from the meteorologists who said that they wanted to be able to see clouds at night in the visible. And they knew from their experience that if they could see the clouds in the visible and the long wave infrared, that they could make a better weather prediction. The long wave infrared works daytime or nighttime. But if you turn on a normal instrument with visible channels for observation of reflected sunlight, if you turn it on at night, you won't see anything. You really have to get the detection limits down quite low. And VIIRS is able to do that. DMSP was able to do that. And so when there's moonlight present, you can easily see the clouds. And here's an example in the Philippines where you can see clouds over here, moonlit clouds. This looks like moonlit fog here. Oops. And so you can also see the lights from Manila and all these other little lights and strings of lights. And so it's a hugely rich data source on human activities that are associated with the production of light. Now, this capability started in the 1970s, believe it or not. And it was with a US Air Force meteorological satellite program. However, they wrote the data to film and there was no digital data preserved until 1992. And so that's when the digital archive for DMSP data got started. And Kim Baugh and I arrived at NOAA, National Geophysical Data Center, in 1994 and began to work on making global products. Of course, the OLS is it's a very crude instrument compared to what we have with VIIRS. Believe it or not, it has only 6-bit quantization. So that's 0 to 63. It has coarse spatial resolution and limited dynamic range because they were interested in the reflectance of moonlight off of clouds, and they really weren't concerned having the dynamic range go out to the brightness levels of cities. And so it's very common to have saturation on bright urban centers. You know that the light's there, but you don't know how bright it is. Now, a lot of these shortcomings of DMSP were addressed in the design of VIIRS. And the first VIIRS was launched in 2011, began to collect usable data in 2012. The second VIIRS was launched in 2017. It began to produce usable data in 2018. And as I understand it, there are going to be 3 more. So we're in line to have a couple of more decades of this type of data available to us, in addition to the data that goes back to 2012. So we make global nighttime light products, And we do pre-filtering of the incoming data that goes into these products to screen out clouds as best we can, solar contamination, which is common in summer months at higher latitudes. And what we aim for is to calculate a stable average. We make these products using reference grids. And so the reference grid for DMSP, because it has coarser spatial resolution, is 30 arc seconds. For VIIRS, we work at 15 arc seconds. We make monthly products where we filter out sunlight, moonlight, and cloudy data. But those products still contain fires and things like aurora and the background. We make annual nighttime lights, and those start out similar to the monthly products, but then we go on to filter out these extraneous phenomena like biomass burning and aurora, and then the background. The gas flares propagate into these products, but we have a separate study on gas flares. So we have year by year, we have lists of gas flaring locations that we make with a set of infrared channels. Now, we have a DMSP annual time series from 1992 to 2013, and we developed methods to make annual nighttime lights from VIIRS and made that for 2015 and 2016. And then we've had a gap for a number of years due to the lack of sponsorship. But we've finally figured a way to make the annual VIIRS nighttime lights products from the monthlies. And while we have a gap in our annual production for VIIRS nighttime lights, we were able to continue the monthly production. And so the monthly production goes back to 2012. And currently, I think there's 96 months available for open access. So here's our set of DMSP nighttime light products. It's organized, those vertical columns you see are the individual satellites, starting with F10, 12, 14, 15, 16, and 18. And in some years, there's a single product. In other years, there's two products where there was usable data from two satellites. And here is the overpass times for, these are actually the equatorial crossing times for the DMSP satellites, and VIIRS is on here too. And note that this is going from noon, down here at the bottom left-hand corner is noon, and up here is midnight. And so VIIRS collects middle of the afternoon, around 1 or 2 o'clock in the afternoon. Then it comes over at night at about the same time. Then the DMSP, you have a series of dawn-dusk satellites that are really pretty much useless for global nighttime lights because there just isn't enough nighttime data. They're focused on tracking what we call the terminator between dawn and dusk, between nighttime and dawn or nighttime and dusk. Then up here are the DMSP satellites that collected at night. And what we found is that if they collect after about 7:30 at night, there's enough global data in a year to make a product. And the reason we stopped in 2013 is because satellite F-18 its orbit had degraded to a point where we no longer could get enough nighttime data to make a product. And so the DMSP satellites didn't have good orbit control, and so their orbits would degrade over time. VIIRS is very tightly controlled, and so we don't have this problem. Okay, so we're working on an extension of the DMSP time series, and this is based on the fact that several of the DMSP satellites that we used many years ago to make annual products, their orbits degraded, we quit using them, and those orbits kept degrading and degrading and degrading until they started to finally collect good nighttime data in the pre-dawn hours. And so here they are, satellite F-18, F-15, F-16, and F-18. They're collecting data in, say, between 2 and 4 in the morning. And so we found a sponsor to get us the staff time to make these products. And so we've got quite a few of them done already, and we're scheduled to get them all completed, I think, by mid-year. And so that's going to make it possible for researchers to do a better job at crossing these satellite boundaries from DMSP, the early series, VIIRS, and now DMSP in the pre-dawn hours. So we're really excited about that. Now, we're also making annual VIIRS nighttime lights products with monthlies. And so it's a little bit different processing stream than we had with our original annual VIIRS nighttime lights products. But I'll show you that the results are very comparable to what we had in the previous processing system. Now, I show you this image. It looks so messy. Well, this is the max. This is the max of the radiances from 12 months. This particular one is 2019. And so now I'd applied a contrast stretch so that you can see all the noise. And so it's only a couple of radiance units between the dark and the light here, but you can see what's buried underneath the data. That you can see the lights, but then you see in the south there's aurora. In the north there's aurora, and then you see these skid marks here. That is where the stray light correction didn't get all the sunlight clipped out. And so those are buried in the monthly composites. And so we've developed procedures to deal with that. A couple of other things, you can see fires here in Africa. And notice right through here between South America and Africa, there is, the data looks more noisy. And there's a reason for that. And I'll show it to you in a moment. So what we discovered is that we can quench a very large portion of that noise by generating the median of the 12 months. And so that way you skip over the extremely bright data that may be flawed in some way, and you skip over the extremely low radiances that may be associated with undetected clouds. And so this is the median for 2019. And so you can still see there is lighting from the aurora. Actually, you can see terrain features. So this is lighting coming from the aurora and then reflecting off the Earth's surface. And so it's still there, but we've knocked it back down to a level that we can deal with it. And the way we filter the background in these products is with a data range. And it's a 3x3 tile that runs over the whole image and calculates the max minus the min radiance. And so we take the median, the 12-month median, and we use that to calculate the data range. And what we discovered is something that we knew from our previous production of VIIRS nighttime lights, is that the threshold for the background is not constant. And that in fact, it is highly correlated with the number of cloud-free coverages. And so for our new series, we're generating, what we've got are, we made a multi-year percent cloud cover. That's this image right here. And the little green boxes are where we extracted samples. And we're trying to get a wide range of cloud cover levels. And we go to the data range image in these sample areas, and then we can make a scattergram. And so here's the scattergram. It shows percent cloud free on the x-axis and data range on the y-axis. And you can see that where there is high levels of cloud-free coverages, the data ranges are very low, and that as you get to lower and lower levels of cloud-free coverages, the data range that you need to separate the background gets higher. And so we fit a curve to this, and we use that same curve to separate the background from lit areas for all 8 years, 2012 through 2019. And so in our previous processing, those thresholds could vary for an individual grid cell or an individual city, but now we've got it stabilized so that we're using the same data range threshold year by year for the individual grid cells. And this is what we get as a final product. And so we've zeroed out the background. We've done our best to preserve the lights. There are still small rims around the lights associated with the glow, the atmospheric glow, but it's definitely, we've got the vast majority of the background zeroed out. We've got the aurora zeroed out as well. Okay, and now let's look at the new product versus the original product for 2015. And so here is Seoul, Korea, and we've got two different versions of nighttime lights. And so we can look at the radiance levels of one versus the other and see what we get. And it's this diagonal line. And so here's the original product, radiance units. And for the same pixels, here's the new product with radiance levels. And so you can see there's a very strong correlation between the two. There are, here you can see this little spike down here. Those are pixels, or rather grid cells with lighting detected with our new product that were missed in the original product. And that's one of the things we strive for, is to detect as much of the genuine surface lighting as possible. Okay, so here's data volumes. And I won't spend too much on this, too much time, but for each month, we're processing about 942 gigabytes of data, ingesting that. And when we make our monthly products, we have a cloud-free coverage, a coverage, and average radiance that make 22 gigabytes. Now, in the new annual products, we're making more than just the average radiance. We're making the median, the minimum, the maximum, the masked median, where we've zeroed out the background. We take that mask and apply it to the average, so we get a masked average. And so we've added to the number of products that we make for the annuals. Okay, so what are nighttime lights measuring? Well, it's obviously the surface lighting, but you can also consider it to be a sample of the electric power consumption. The International Energy Administration, International Energy Agency, in a report from, I guess, about 15 years ago, found that 19% of electric power supplies worldwide are used for lighting. So, in fact, we're sampling we're getting a sample of the electric power consumption. And things that you can see, these data get used by a lot of different scientists. They show up in media as well. But here's an example where you can see the growth of detected lighting in northern India year by year. And you can see in 2013, going to 2016, there are a lot of dark areas here that have been filled in with lighting, and even stronger lighting in 2020. So there's a lot of things to see in these data sets. Okay, now I'm going to talk about the work that we were doing where we discovered the annual cycling patterns in India. And we discovered this in our research that we're doing for the Rockefeller Foundation on the remote sensing of power stability. And we wanted to dig deeper into what's in this nightly data. And so instead of working with annual or monthly data, we worked with nightly data, and we assembled long-term profiles. And we did this in a grid pattern over a number of cities in Africa, Asia, and USA, and did a study on indices that can be indicating some instability or deficiency in the power supplies. And this particular grid is in a place called Gaya in Bihar in India, northern India. And so there is a temporal profile for each of these grid cells. They're on 15 arc-second spacing. And here you can see the temporal profile over time, starting in 2012 and going out to through 2019 and into 2020. And you can see an annual cycle. Now, the analysis method that we picked up on to determine which grid cells have cycling is called the autocorrelation function. And here's the chart for that. It says ACF on it, and it reports the correlation between the images or the radiance levels for this individual grid cell as a function of time. That is, where does it sync up and where is it out of sync? And so the lag reports is reported here in days, and you can see that there is a prominent spike at about the 1 year mark, 365 days. And so that's our tip off that there is cycling, annual cycling in this grid cell. But we found several different patterns. Here's a pattern here where you can see there are 2 spikes. Now, I forgot to mention that in the background, you're seeing the autocorrelation function for the original data prior to correction for lunar illuminance. And so what you're seeing there is a 29-day cycle that's associated with the moonlight. But we developed a method to subtract off the lunar reflectance component, grid cell by grid cell, and then we can see the annual cycling much clearer. And so in this case, there are 2 prominent peaks. There's one here at about the mid-year point, lag of looks like about 100, perhaps 170, 160, 170. And then there's a spike out here closer to the 1 year mark. So that's a new pattern that we found, and it's indicating that there are 2 cycling phenomena each year. And then we also found these, which we call acyclic. And so there's no prominent peak in the ACF profile. And if you look at the day-night band profile, you can see it's scattered, but there's no annual cycling. So we've been working with this, and we wanted to see, does this also show up in the monthly data? And the answer is yes. We can see these cycles in the monthly data. And that's good news because we have global coverage with the monthly data. And the nightly profile grids, we've only generated for test sites. And so if we can see this cycling in the monthly data, then we have a shot at making products related to annual cycling for entire continents or perhaps global. And so here's a case. This is in northern India, and I've put some labels on here. You can see that there's a drop in radiance each year, and it's in the summer months. There are, the peak radiance is generally in the fall and in the spring. And in between, there is frequently a minor dip in radiance that's in the winter months. And so the dips in radiance are occurring in summer and winter months. The summer months, the dip is stronger, but there really is one in the winter months as well. Now, this is probably the month of Diwali. That's November 2012. And so currently we know we have a calendar for the month of Diwali, the Festival of Lights. And before we do this autocorrelation analysis, we interpolate through the Diwali month. And so we're trying to reduce the influence of Diwali on annual cycling. Not every grid cell has that Diwali bump, we call it, but as a precaution, we wanted to address that so that we're actually seeing annual cycling that is unrelated to Diwali. Okay, now looking at the monthly autocorrelation profiles, we see the same patterns that we saw in the nightly data. We see what appears to be a single cycle with a prominent peak out around the 12-month lag. This one says 13. There is, oh yes, I remember. This has here, this is lag 0. It says band number, but it's actually lag. So band lag of 0, by definition, has an autocorrelation function of 1. And so this is actually ACF1, and that peak there is actually at ACF12, so it's the 12-month lag. And so I didn't adjust the scaling on the x-axis, but this is the 12th month. And so we can see that we also have the double cycle pattern, and then we have the acyclic pattern. And so we built a algorithm that can distinguish these 3 types, and then we can make a map. And oh, okay, so here, this is a red, green, blue composite using autocorrelation for month 12 as red, month 9 as green, and month 6 as blue. Let me go back. And so you enhance the contrast, and you see these various hues, which are related to the cycling. And so you can see this crimson red up there. That is where Jammu is, and that has a really prominent peak at ACF12, or lag of 12 months, and nothing else. And so where you have, that comes from the ACF12. The magenta colors here means that you're seeing a ACF peak in ACF12, ACF peak in ACF12 and ACF6. So that's red plus blue is giving us those magenta colors. And then there's some orange in here that is coming from ACF12 and ACF9. So you can do some photo interpretation, but then we went on to actually label each grid cell for what type of cycling it had. And let's see, here it is. And so the areas that had a single prominent peak at ACF12 are red. Areas that had the 2 peaks are blue, and areas that were acyclic are green. And so you can see that the green is concentrated in southern India. And so it's an indication that they have more stable power supply throughout the year. And the red and cyan are primarily in northern India. And so it is definitely showing something about the cycling pattern. We believe it's related to load shedding, which is a way to shut down power supplies during periods where there's a shortfall, basically a mismatch between supply and demand. But you can also look around. You can see, for instance, Karachi also has a very strong cycling at ACF12. Over here in Myanmar, you can see Yangon also has that pattern. So we know as we go around the world, we're going to find places that have annual cycling and other places that don't. So we think there's going to be some interesting stories coming from this, and it's something that we're currently working on. So these are the cities where we have the day-night band profiles, nightly data in those grids. And this is the percent in each of those study areas of grid cells with annual cycling present. And you can see in India, Delhi and Gaya, it's over 50%, almost 70% in Gaya. There are some other places that have quite a bit of annual cycling: Pyongyang, Dhaka, Shanghai, Seoul. And then there's places that have very limited annual cycling, down around 10%, such as Houston, Wuhan, Beijing, Harare. When we expand this to global, we're going to find which areas have the annual cycling. It's interesting that even in developed countries, there are some grid cells that have annual cycling, and we haven't figured out what that is coming from, but that's part of the fun. Okay, so here's my summary. We're extending the DMSP time series from 2013 to 2019, and expect to have that time series released for open access in 2021. We've developed a new method for making annual VIIRS nighttime lights, and we have those products in preliminary form from 2013 to 2019. We're polishing them up and writing a paper, and so we expect that those would be released also in 2021. We've discovered annual cycling in India, and we think it's associated with load shedding. We first found that annual cycling in nightly day-night band profiles, but discovered that it is present in the monthlies. And we're working on methods to recognize the style of annual cycling, and those also to recognize those grid cells that lack the cycling. So I think that's all for now. Perhaps we have a little time for some questions or discussion.
Yes, we do. Chris, thank you so much for this fascinating talk. And I have tons of questions, and we have many questions in the chat, and we have only 3 or 4 minutes. So let's prioritize the questions in the chat. And the first question relates to the difference between VIIRS and DMSP-OLS. Whether with VIIRS data, we can differentiate between different types of land cover and land use in dense urban areas. What are the advantages of VIIRS data versus DMSP-OLS when looking at cities?
Okay, well, if you look closely, you'll find that the OLS is very much, in almost every way, a cruder instrument. It has the VIIRS footprint of the individual pixels is 45% smaller, so much higher spatial resolution than we had with DMSP. And the detection limits are comparable, but we've tested and see that VIIRS actually has lower detection limits than VIIRS, rather than DMSP. So what that one of the consequences of that is that VIIRS can detect smaller light sources than DMSP. Now, the light source doesn't have to fill the full pixel footprint. In fact, we found that the VIIRS can detect a 1,000-watt light bulb inside of a pixel. And so it is obviously not filling the full pixel footprint. That if it's a strong emitter, it can be detected even in a sub-pixel format. The other thing is that VIIRS has in-flight calibration and has such a wide dynamic range, we've never seen saturation on urban lights. So there's a lot of advantages to the VIIRS over the DMSP. if you have a choice, that's a good place to start with the VIIRS because it's a higher quality data source. Does that answer?
What about detecting low density rural areas? Can VIIRS actually detect low emission and villages?
Well, it has some capabilities in that regard, but there's always detection limits. And so I took a close look in India recently, looking at our new nighttime lights data set. And I looked at it as an overlay in Google Earth where I could zoom in and see the villages, and some are getting detected, others are not. So it's still not got everything that you'd like to have there. Now, I have no ground truth, so I don't know. Maybe those villages that were not detected, maybe they're not electrified. I don't know. But I could see that there are lots of detections, lots of cities and towns and small villages that do have detection with VIIRS, but there are others that don't. And so there are obviously the smaller places, and we haven't had a chance to fully investigate that, but we know that it's a consequence of detection limits.
Okay, and we have a few questions related to the cycling in nighttime lights that you talked about, the seasonal variations. What are the causes? How can one deal with it? How can one infer, something about the actual economic activity and not pure noise?
Yeah. So, I view this cycling as a consequence of a instability in the power supply that it's appears to be associated with a phenomenon called load shedding. And so obviously the infrastructure is still there. Probably the economic activity is still there, but there are periods of time when the power is not available. And obviously that's going to be a drag on the economy, but the reason we're studying it is because we want to be able to rate the stability or adequacy of power supplies and to track that through time. And so that's one of the things that we're investigating is, can we detect changes in the amplitude of this cycling? That where is it basically the question is the load shedding diminishing, or is it just as strong as it's been for the past 5 or 6 years?
Okay, great, thank you. We have 13 more questions and we don't have enough time. So maybe the last question would be, how do you see the future of nighttime lights? What are the advancements that you predict in this field? Is it spatial resolution? Is it temporal resolution? Is it new algorithms that can better predict socioeconomic variables?
Oh, yeah. So, I've thought about that. I think there are a couple of things. One is enhanced spatial resolution. So there have been several satellites that have collected high spatial resolution nighttime lights data set. I haven't kept up very closely on that, but I know it has happened, but it hasn't gotten to a point where you can get nightly global data. And so that's one of the advantages of VIIRS, that you're not looking down at the Earth through a soda straw, you're getting global coverage every 24 hours. Now, another area where I'm sure that there will be advancements is in terms of getting multispectral or hyperspectral low-light imaging data, where it will be possible to identify the type of lighting from LED to high-pressure sodium to metal halide to incandescent, and also how the installed lighting changes over time in terms of type. We know that there's some places that are converting to LED. And so with multispectral data or hyperspectral low light imaging data, you'd be able to see that. So I think those are the major advances that we can look forward to. I don't know how long it will take, but I think those are obvious directions for improving the quality of nighttime lights, is improving the spatial resolution, perhaps improving the temporal resolution. Right now, we're working in terms of temporal overpasses. We've got satellites that are primarily designed to serve the meteorologists. And so VIIRS comes over at between midnight and 3 o'clock in the morning. And that's probably not the best time to look for lights. It'd be better to have your overpass, say, between 8 o'clock and 10 o'clock at night. So I'm sure there'll be advances. But for now, we're just trying to squeeze as much value as we can out of the records we have from VIIRS and the older records from DMSP.
Okay, great. So Dr. Eldridge, I have no words to thank you so much for this fascinating talk. As someone who has been working with nighttime lights for quite a few years, I admire your work, and thank you for your contribution to this field.
Yeah, thank you very much. Anyone who's on the call, feel welcome to send me an email with your questions, and we're always interested to see the use of these products expanded. And it's been really gratifying to see that there are literally thousands of papers that have been written using these data sets.
Great. So I will hand it over to Trevor Monroe, who will lead the next panel. So Chris, thank you again so much.